and this one's Biotech, but I know there's a whole series and they all are about the leading edge of technology. And so I don't have to sell you on the idea that technology has been moving at an alarming pace. And I think I probably don't have to sell this audience on the fact that the technology has changed in very, very fundamental ways many things about human culture at a level that has never happened before in the history of the human race. I wish I could report that the wonderful onward march of technology had done the same for science itself. Let me explain what I mean. We were talking over dinner about ontology recapitulating phylogeny. And that is more true in education than in any other endeavor. What happens is that certain scientific things were invented, discovered, put forward down through history. They became accepted, and then they got to be what was known, and the field went on. And there's nowhere where that phenomena is more evident than in our understanding of physical law. So while our technology has taken what understanding we have of physical law and gone gangbusters with it in the information technology, which Gordon was talking about, but also in the biotech that you heard about today, we don't see that remarkable advance in what we teach our high school students, what we teach our undergraduate students. So let me go back and talk a little about how we got here. You, of course, all know that the Earth used to be the center of the universe and everything revolved about it. We don't think that anymore. And you knew there were 4 elements in the periodic table, didn't you? Earth, air, fire, and water. Everybody knows that. And phlogiston, thank you, that's a good one. Yeah, fire used to be phlogiston. That was a separate thing. And we'd laugh. They're ludicrous. But you know, if you go back and read what those people were talking about, they weren't stupid people. They were very smart people. They were just stuck in a way of thinking. And that was only a few hundred years ago. So let me ask you, what do you think people would be laughing about 100 years from now that we're teaching our kids today? So that's what I want to talk about. The physical laws that I'm going to group are really started with Galileo. And Galileo used the technology he had available in Italy. You could get very nicely made marble spheres, and you could get very nicely made marble slabs. And he did a bunch of experiments where he rolled marble spheres down marble slabs, and you could make angles in the marble slabs. And he discovered an amazing thing, that if you rolled a marble sphere down a marble slab onto one that was flat, it kept rolling. Now, let me remind you that in that day, Aristotle and everyone said if something kept moving, there had to be something keeping it moving. Like when the things in the heavens went around the earth, because the earth was the center then, remember, there had to be something taking them around. In those days, it was a flock of invisible angels that carried them around. That was what you had to have. We don't think like that today. Galileo observed that if you got the thing rolling, it'd just keep rolling. It's a new idea. And then it became one of Newton's laws that state of motion, it would stay in a state of motion unless you did something to change the state of motion. Well, what would you do to change the state of motion? Well, Newton said you use a force. Well, what's a force? Well, you push on the thing. Don't you see? Oh, that's a force. All right. So what do we do? Now, introductory physics. The force equals the change in momentum. Okay? That's mechanics, most of it. All right, that's fine. The next thing that happened was electromagnetism. The big breakthrough there was Faraday, who discovered if he wrapped wires around a ring of iron and put a battery across the wires, that nothing much happened until he took the wire loose from the battery and there was a big spark. What's that about? Then he did a remarkable experiment. He had this ring of iron, and he wrapped a coil around one side of it, and he wrapped another coil around the other side. And he found that if he put the battery on one of those coils, and he put a couple of little points on the ends of the wires of the other coil, and then he unhooked the battery, and there was a spark across the points on the other coil. So he invented the transformer and invented or discovered what became called the law of induction, which is the reason we have the age of electricity. So it was the change in current in the coil that caused the voltage. Okay? You see a pattern emerging? Newton said, if I'm going to change the momentum, I use a force. And Faraday said, if I change the current, I get a voltage. We're starting to think that all these physical laws are about changes. Well, if they weren't, what would you do? How could you measure anything if you don't measure a change from one state to another? Of course it's about changes. Okay, that's fine. Well then, just about as that was settling down, there was a young fellow by the name of Max Planck who went to his advisor in Germany. It's in the last decade of the 1800s. And told his advisor he wanted to do a thesis on electromagnetism. And his advisor said, that's all worked out. The only thing you'll do is just put more decimal places on all the stuff that's known already. Don't do it. Nothing left there. Well, he didn't listen to his advisor, and he went off and started trying to understand this stuff. And of all crazy things, he was studying irradiation from hot objects and noticed that the prevailing theory of the day just didn't work. And he said later he was prepared to give up everything he knew about physics to figure this one out. And that was the first hint we had of what we now call the quantum theory. That somehow electromagnetism wasn't the nice continuous thing that we had thought it was, and that electromagnetic radiation came in these little quanta. And a few years later, Einstein said, suppose it was true that electromagnetic energy is like a little bullet. It carries a certain energy that's proportional to its frequency, and it carries it off in a certain direction until it hits something that absorbs the energy. Well, Einstein was pretty brash at the time, and he could put that forward. He would regret it later. But that started the whole kit and caboodle of quantum physics. And then you've probably all heard that there were lots of disagreements, fights, misunderstandings, which persist to this day about the quantum theory. But before the fight got really bad, Einstein went off and did a side project on gravitation. And it turned out to not be as simple as he thought. And it took him about 10 years to get anywhere with that. And he ended up in 1915 coming up with this general theory of relativity, which you've all heard about, which is the theory of gravitation that we use today. And it has the very odd property. Well, it started with a very simple statement. Already in 1905, Einstein had made what he called the special theory of relativity by postulating that the velocity of light is constant in whatever frame of reference you're in. And that worked so well that he went beyond that and said, you don't just have to be in frames of reference which are going along nicely. you could be in a frame of reference that was accelerating if you used the right mathematics. And the mathematics he used were the mathematics of curved space-time. If you decide that the velocity of light is constant, and it turns out not to be, there are two things you can do about it. You can either admit that it's not constant, or you can warp space and time to make it constant. Well, he chose to do the latter. Okay, it worked. It's working to this day admirably. Well, a few years later, Einstein started getting into fights with Niels Bohr about the quantum theory. And that led to a series of very serious disagreements. Einstein had worked on electromagnetic radiation ever since this 1905 thing where he'd published a little bullet of quantized energy. So he knew about it. And he got in a fight with a guy by the name of Ritz. And what Ritz said is that light just propagates in one direction. If you send out a flash of light here, it just goes and goes until it hits something. And if it doesn't hit anything, it just keeps going. So when you push the button on your flashlight, that energy goes into the electromagnetic wave, and that just goes. So the conservation of energy and the sort of one-wayness of energy is a property of electromagnetism. And Einstein said, no, that's not what happens. That electromagnetic radiation, the laws that we know of electromagnetic radiation, treat time equally in both directions. So he said something very deep. He said, you can explain electromagnetic energy transfer either by keeping track of all of the electrons that are rushing around generating the wave, or you can keep track of it by what all the electrons are doing that are absorbing the wave equally well. The law is symmetric in that way. But preferably, you would realize that half of it's due to the electrons that are generating the wave, and the other half is due to the electrons that are absorbing the wave. That was his preferred way of characterizing. You can write it all three ways, but that was the one he thought was the most illustrative of what was going on. Nobody paid the slightest attention. Not the way electromagnetism is taught to this day. It was a very deep insight. Well, on we have gone. After the fights on the quantum theory settled down, you've all probably heard about the debates that Einstein had with Bohr, and he lost them. Had two of them, and he lost them both. Bohr was a very strong personality and a good debater. Einstein would rather understand what was going on than win the debate, so that wasn't an even match. But after that, what happened is Bohr and Heisenberg and Dirac had come up with some mathematics that allowed you to solve problems for quantized energy transfer. And some of the guys that had been in earlier, like de Broglie and Schrödinger, who had characterized the nature of the electron and other matter as a wave, got sort of left behind because you didn't need that characterization to do the mathematics. So this was a case where we had started out having a physical picture of the electron as a wave propagating around the proton. And that's why it had discrete energy levels. It all made perfect sense intuitively. But then you got some fancy mathematics that made it unnecessary to have the physical picture. And then Bohr argued that we're above all that now. We don't need physical pictures. We don't need to use intuition. In fact, only people that are a lower form of life would use any physical reasoning like that. And we're above that. We just use mathematics. Now, don't get me wrong. There's nothing wrong with mathematics. But what got propagated was the notion that mathematics had become the guide to physical theory. Now, a lot of you know a lot about mathematics. I don't have to tell you about that. But one of the things that I've developed down through my life is an enormous respect for the power of mathematics. I know a lot of mathematicians. They're very bright. And one of the things I've come to realize is that you can, if you're good enough, develop a mathematics for any physical theory, whether it's what nature does or not. So in fact, if you say that mathematics is going to guide what physics does, all you're saying is that you've let go of the fact that what the real world does should be guiding what your physics is, because the mathematics can express anything. Well, that's where we are today. Mathematics took over, and we now have essentially all of our physics taught with increasingly sophisticated mathematics and less physical insight. And that happened since the late 1920s. Meanwhile, there have been fantastic, amazing experimental results. The technology that we work with today is the result of a bunch of people not doing mathematics but doing experiments and figuring out how nature really works and putting it to work doing electronics and optics and biology and all kinds of marvelous things. So I asked myself the question, if we knew what we know today, experimentally, how nature works, would we teach our youngsters about physics the way we teach them? And I think we absolutely would not. So that's what I'd like to share with you tonight, is why I think that. One of the things we've learned about quantum systems is that the way they're coupled has nothing to do with a force. If you just write down any of the wave equations, the Schrödinger equation or the Dirac equation or any of the wave equations that represent elements of matter, electrons or protons or neutrons or whatever, you will find that there are two terms in the expression for the momentum of the electron, let's say. The first one has to do with how fast it's going, and the second one has to do with how fast other electrons are going. Or said another way, the momentum of every electron has the momentum of every other electron in the universe in it. Now just think about that for a while. That's an amazing thing. There's no force in that. Now, if you want to make it into a force, you say, well, I change the momentum of this electron, and that changes the momentum of this electron. So it's equivalent to a force. But it's a much more fundamental statement of what's true. Because the force is about a change in something, and the actual law is about the relation between the two. The way we're teaching our students is one full derivative away from the physical law. The same thing happened with electromagnetism. When Maxwell did his original treatise, which are amazing piece of work, he worked out all the interactions, magnetic interaction and the electrical interaction, using what he called the potential. And the potential had two parts, what we call the scalar potential, the electrostatic potential, which is why two charges either attract or repel each other. But then there's a vector part, and that's how one current affects another current. A current is a flow of electrons, and it's a vector. It has a magnitude and a direction, and that affects other currents by a vector interaction. And those two potentials say what I just said, and this was long before the quantum theory, but they say this current has in it every other current in the universe. It's a much deeper statement. Well, Maxwell got some followers that had really good ideas, but the followers believed in the ether, and I'm not talking about putting anybody to sleep. In fact, I hope not to tonight. It was a substance that was supposed to permeate all of space, and you couldn't detect it except that's what light went through, because people couldn't imagine a wave propagating unless it had something to propagate in, like it had to propagate in air or in water or in glass or something, but it couldn't just go by itself. That wouldn't do. So they took out all these potentials that Maxwell had come up with, and he actually sort of gave him permission to do that. And instead we got derivatives of the potentials, because they thought of those as the distortions of the ether. And we call those distortions the magnetic field and the electric field, and you all probably got drugged through courses in electromagnetism that gave you E's and B's and curls of curls and all of that wonderful stuff that most of you didn't go back and use a lot. And probably nobody ever told you that what's really true is the momentum of every electron has the momentum of every electron in the universe in it. Well, one of the reasons we don't hear that is that electrical substance, electrons, protons, we have as many protons as we have electrons. So on average, the energy is such that the positive charges attract the negative charges and either make themselves into atoms or they make themselves into a metal or have as many electrons as protons. And you don't have large quantities of charge out there all by themselves. And so they sort of average out to zero over large distances. And locally you can have some currents or some charges, and of course when we do engineering we do that all the time because that's how we build things. But on average, if you go to a big enough space, you don't have any average current or any average charge, and so we don't have to worry about it. But with gravitation, if we could just shift our attention to that for a minute, there's only one sign of what people call mass. And we know that it attracts other masses. That's why we're in orbit around the sun and all those such things. That's why when you drop a rock on your foot, it hurts. So with gravitation, it was thought very early on that maybe it worked the same way as electromagnetism. Maxwell thought that. Heaviside thought that. A lot of people have thought that thought. It's hard to miss. So what's wrong with that? Well, the first thing that happens when you do that is you notice that the potential energy, goes down when two masses come together. So if you have a bunch of mass in the universe, the potential just goes down and down and down, and it goes negative. And what is the meaning of a negative energy? Didn't make any sense. That was the big thing. Then there were some proofs that it couldn't happen because of some technical stuff, which I won't drag you through. But the big thing was, we didn't know about the expanding universe. That wasn't discovered till the 40s. So if you have an expanding universe that came from a Big Bang or wherever, there's a lot of energy in it. And if slowing it down makes the energy a little less, that's just fine. So you see a pattern here that certain ideas that might work today wouldn't work back then because we didn't know about an expanding universe. We didn't know that electron wave functions were coupled by the momentum of one being in the momentum of the other. We didn't know any of that. That came later. So let's just go back now to the time of Newton and say, okay, yeah, we can make a force out of things if we want, but let's call it a potential. That matter attracts other matter by the fact that the potential gets lower as they get together. That's what happens when you take a positive charge and a negative charge. It's why they attract. And let's say it happened just the same way when you bring two masses together. That's why they attract. Well, if that was true, they would also have what we call in electromagnetism the magnetic interaction, the vector part. And if that were true, you can just sit down and work out the consequences. Suppose we have this quantum interaction between every element of matter that's both electrical if they have charge, and if they don't have charge, you still have the gravitational part. Suppose you just sit down and work that out. Well, what happens is you find that you get the usual attraction of, you can keep things in orbit and all, but you start getting little corrections to that. For instance, you find that if you have an orbit of a planet around a star, if it's an eccentric orbit, it won't stay still. It creeps around, you know, the thing goes around and it doesn't quite come back on itself and it creeps around. Well, that turns out to be exactly what general relativity predicts. That's interesting. So you can work out all of the experiments that have been done to prove that general relativity is the right theory of gravitation. And when you do, what you find is that you can predict all those same things by this vastly simpler way. That gravitation works just like electromagnetism, but using this coupling that every element of matter has the momentum of every other element of matter in it. If you don't do that, you get tangled up in the fact that you have one too many derivatives, and that throws you off. But if you go back to the most fundamental thing we know, it all works. I was very surprised to learn this, and of course I went and talked to my friend Kip Thorne, who has just become famous because he did a movie. He's done wonderful physics all these years, but nobody knew about him until he did the movie. And I said, hey, what's going on here? Does everybody know this? And he said, no, nobody does it this way. So, okay. So, well, simplicity used to be valued in the field of physics until the value system started valuing the prettiness of the mathematics rather than the simplicity of the physical reasoning. So you have to have something more than just being able to do these horrible complex problems in a very simple way and being able to explain to students that are first learning about electromagnetism and gravitation how that works in a very simple way. That is no longer enough to convince anyone. So of course one has to ask oneself if this very simple thing you've come up with predicts anything different than general relativity, because that would be exciting. And the answer is yes, it does. And this is where it gets exciting in the present. It turns out that just as if you take electrons and protons, positive and negative charges, and do this with them, they will radiate electromagnetic radiation. We do that all the time. We all have devices on us that do that. If you take two masses and rotate them around each other, both this very simple theory and general relativity predict that you will radiate gravitational radiation. It just works exactly like electromagnetic radiation, but it's gravitational in origin. So its origin is the amount of matter, not the amount of charge. When you work that out, it's very interesting that general relativity comes up with a different radiation pattern from, my example, a binary star than you get if it were an antenna and it was an electromagnetic radiation, or if it's this very simple way of doing gravitation. Well, that's nice because you can show that the two theories are not totally equivalent, although they give all the same answers at first order to these so-called tests of general relativity. But, you know, you can't take the binary star and turn it on edge and show that the signal is radiating goes to zero. It's not an experiment we can do. But what we can do is we can take the antenna that's sitting on Earth that we're using to detect gravitational wave, and that goes around because the Earth is going around. And so there'll be places where it has a maximum of signal that it gets from whatever source there is out there, and then it'll go through zero, and then it'll reverse sine, just like an electromagnetic antenna. And when we're able to see signals from things out in space, we'll know. We haven't seen a gravitational wave in any of our gravitational wave detectors yet. The most advanced one right now is LIGO. There are two installations, one in Louisiana and one up in eastern Washington. And they're just being upgraded. They're right now running at about 3 times the sensitivity that they had before the upgrade, and they're scheduled to be about 10 times the sensitivity when they're done. It's a coherent detector, so that means 1,000 times more potential sources out there. So, good chance in the next 5 years we'll have gravitational wave signals. And when we do, we'll be able to tell if this approach to gravitation gives the right answer or if general relativity does. And I never thought I'd be in a situation where I went in a shootout with Einstein. He's one of my heroes. On the other hand, I think he would like it. So stay tuned.